Hello WinCraps fans. As you may know, WinCraps can generate dice rolls from a number of different sources. One of those sources is something called a random number generator, or RNG. Technically, it's a PRNG, which stands for pseudo-random number generator. It's called a pseudo-random number generator because the numbers it produces do not come from a real random source. Instead, they come from a mathematical algorithm, which is a deterministic process. Each time a number is requested, the PRNG takes its current internal state, runs through a process, and generates a new number. So if you know how the algorithm works and you know its current internal state, you can actually determine what the next number will be. Fortunately, the algorithm is complicated and hidden from view, so you probably don't know how it works and you probably don't know its current internal state. So for all practical purposes, the numbers you'll receive are unpredictable. Additionally, the mathematicians have come up with some PRNGs which are perfectly suitable for simulation, having superb random-like qualities. Indeed, even the casino industry has expressed their confidence in PRNGs by utilizing them in most of today's electronic slot machines. In cryptography and critical high-value situations, you need true randomness. But in a dice simulation, you only need unpredictable numbers exhibiting random-like qualities such as unpredictable streaks, clumps, and voids. Fortunately, WinCraps gathers numerous statistics, so we can see if the numbers it produces have these characteristics. Let me stop the rolling right here and let's open up the AutoBet screen. If I showed you a couple sequences of numbers, could you tell which is real and which is simulated? How about 62587 versus 759312? Kind of hard to tell, isn't it? How about 49248 versus 77777? Would you say that the first sequence is real and the second is not? Why? Is 5 sevens in a row not possible with real dice? Well, of course it is. Fact is, you really don't have enough information to say which sequence is random. However, if 5 sevens in a row were rolled on average once every 20 rolls, would you begin to suspect a problem? Probably. But would it not be possible to do so randomly over at least some period of time? Well, maybe, but over what period of time? Truth be told, it's actually quite hard, if not impossible, to determine what's truly random, because true randomness includes all possibilities. The subject of random numbers and RNGs is a huge topic which could fill libraries. Nevertheless, using reasonable amounts of data, compiling statistics, and comparing them to probability, we can draw some workable conclusions. So let's do that. Let's start by rolling some simulated numbers and see how they compare to expected rolls. I'm going to open the roll total screen. And I tell you what, actually let's clear this out first. We'll clear all the previous data out. And we'll look at the roll total screen. Now let me explain this here. What we're looking at is going to be a table of data and a graph. This is for the 11 basic numbers 2 through 12. Each time a number is rolled, it's going to get recorded here in this column, number of rolls. Then it's going to be converted to a percentage of the total. The percentage will appear in this column, and then it will be graphed on the graph. It will be a colored bar next to the appropriate number. And it can be compared to the gray bars here, which are the probable bars and the probable percentage. So for example, the number 2, it has a probability of 1 out of 36. That's 2.78%. And the bar here is reflected at 2.78%. Number 7 can appear on average 6 out of 36 rolls. That's 16.67%, and that's reflected on the graph as well. Notice how the graph is symmetrical and triangular. So let's start rolling a few rolls here. And actually, I need to bring that up again. Okay, so as we can see, as we start to roll, the graph starts to fill in. And over time, the colored bars are going to start to grow closer and closer to the gray bars. All right, let's speed this up a little bit. Let's use the hyperdrive and watch to see what happens. Notice how the graph is starting to fill in. It's still bouncing around quite a bit, but it's filling in, and the colored bars going up and down, but over time they're growing closer and closer to the gray bars. Let's close that just for a moment, run the hyperdrive so we can run it quicker. And now let's take another look at the roll total screen. Now you can see after 16, almost 17,000 rolls, the colored bars are getting pretty darn close to the gray bars. So we can see that the actual numbers do conform quite nicely to the expected rolls. Now let's try to compare some simulated rolls from WinCraps RNG number 1 with those from a file called rand.org100k. RNG number 1 is a random number generator called the Mersenne twister. That's spelled M-E-R-S-E-N-N-E, so you can look it up on the internet if you like. And rand.org100k is a file available on cloudcitysoftware.com, a roll file. So RNG number 1 you would select from the configuration screen on the miscellaneous tab in this box right here. Rand.org100k, after downloading it from WinCraps, you would load it here on the dice roll files screen. Rand.org100k, and it shows here that it has 100,000 rolls in it. So the Rand.org100k is from a site called random.org. It contains a list of rolls generated from random atmospheric radio noise. If you want to learn how to collect your own real random rolls from this source, check out question number 17 on cloudcitysoftware.com on the FAQ page. So what I've done is I've rolled out both of these sources over various numbers of rolls and taken some snapshots of the results. So let's take a look at that. So I've separated these into the two sources. RNG number 1, and I've seeded it with a value of 3122022. If you want to open your own copy of WinCraps, select RNG number 1 and seed it with that value, you'll be able to reproduce the same rolls. And of course, Rand.org100k. So the question here that we're going to be looking at is, which of these rolls are real and which of them are simulated, left or right? These samples are taken at 50 rolls, 500 rolls, 5,000, and 50,000 rolls. If we look at the 50 roll sample, we can see there's quite a bit of variation between the probable bars and the actual bars. This first sample on the left actually has an abundance of 6s. The one to the right, we can see there's also quite a bit of variance, and this one has an abundance of 10s. When we get to 500 rolls, we can see there's still a lot of variance, but maybe not quite as much. The graph seems to be filling in a little bit more. The same thing with the sample on the right. It seems to have a similar deviation for these bars as the left sample. At 5,000, they're calming down even a little bit more, and by the time we get to 50,000 rolls, the colored bars are just about perfectly in alignment with all the gray bars, and that's for both samples. So again, which ones are real and which ones are simulated? Well, maybe you feel you can tell with this one sample, and maybe you'd be right. But if we were to compare multiple samples, chances are your selections would be no better than guesses. In this case, the real rolls are here on the left. The key points to note is that with both the real and simulated samples, the shape of the graph bars grow closer and closer to the shape of the probable bars as the rolls increase. In addition, they exhibit lots of variation with little data and little variation with lots of data. Now, how close are the results to probability? There's a statistical test called chi-square, which we can employ to judge the goodness of fit between expected and observed rolls. This test is included in the latest version of WinCraps. You can find it here on the roll total screen. It has a separate column. It's called chi-square. Now, if you don't see it on your roll total screen, then go up to the display menu and you can select it there. What chi-square is a very simple little formula. It takes the observed number of rolls minus the expected number of rolls, squares that value, and divides by the expected number of rolls. It then converts the resulting chi-square numbers into a p-value. A p-value is the probability of observing the displayed values, the displayed or more extreme values. Data that deviates farther from the expected value is more extreme and will have a small p-value. Data that deviates less from expected value is a better fit and has a high p-value. Let's look at a chi-square comparison now of real versus simulated rolls. Make this a little bit bigger. Once again, we have RNG number 1 with that seed and Rand.org100k. Which rolls are real and which are simulated, left or right? Once again, we have samples at 50, 500, 5,000, and 50,000. At 50, there's really not too many rolls, and so we can have all kinds of wild values. We have 38 versus 66. By the time we get to 500 rolls, it looks like they're both around 5%. 5,000, we got 44 versus 21. And by the time we get to 50,000 rolls, both samples are looking right around 46%. So which ones are real and which ones are simulated? Actually, if we were to increase the number of rolls, the probability, the p-value going up is increased. So in this case, the real rolls are here on the right. So we can see that the aggregate numbers seem comparable. But what about special circumstances? A recent viewer claimed that WinCraps rolled too many 2s, 3s, 7s, 11s, and 12s in the come out roll. So let's take a look at that. Open up the AutoBet screen again. We have a file here which has a few lines of initialization, basically just clears some check stacks and names one of them. And then it takes a look and says, if the last roll was a come out roll, then let's record how many come out rolls we're going to see. Of course, that data is available elsewhere in the game, but we're just going to put it here on check stack number 0. That's how many come out rolls there were. And then we're going to use the value of the dice to reference a check stack. So if the dice total is 4, we're going to say check stack 4 is going to be recording how many 4s there were. If the dice total were 12, then check stack 12 will record how many 12s there were. That's it. The rest of these lines are just a little loop that creates a graph on the check stack screen, so we have something to look at. So let me activate this. We're going to open up the check stack screen. And let's see, why is that not showing? Do we start a new game? There you go. Okay, so now it's going to show the number of come out rolls. So let's roll the very first come out roll. So there's one come out roll. It was an 8, and it's drawn down here the percentage. Right now it's at 100%, and it makes a little graph. There's the second come out roll. It looks like we had 2 8s. So let's start the hyperdrive now, and let's watch this fill in a little bit. All right, we'll stop it right around here. That's right around 500 rolls. At 500 rolls, we've seen 136 come out rolls. Out of 136, we should expect to see 3.7 2s. In actuality, we saw 2, so we're a little bit low. We should have expected 7.5 3s. We saw 8, slightly high, but pretty close, etc., etc. You can go through the whole list. Number 7, we should have expected 22. We saw 16, so that's actually quite low. Down here we can see the percentages of what was actually rolled, and we can see that converted into our little graph. You can see that the graph, it's got a little bit of symmetry to it. The outside numbers are less than the inside numbers, but it's not perfectly symmetrical nor triangular. However, if we'll close that screen and run the hyperdrive just for a few moments, okay, there's 10,000 rolls. Let's see what we've got now. At 10,000 rolls, we've seen 3,173 come out rolls, and we can look at the percentages here. 2s were at 83, or not the percentage, the actual numbers. 83, we should have expected 88. 7s were 508, should have expected 528, so it's still a little bit low. But if we look down here at the little graph now, we can see it's getting more and more symmetrical, looking a little bit more triangular. As we continue to increase the number of rolls, that's going to become better and better. So what I've done now is also rolled out the RNG number 1 versus Randorg 100K. And here's the sample I've taken at 50 rolls. One sample has had 11 come out rolls, and you can see what that distribution was and what the graph looks like. Another sample saw 16 come out rolls, and again you can see the distribution and what the graph looks like. So which is real and which is simulated? Before I answer that, let's look at the next sample here. This is basically the same information, only at 50,000 rolls. Now we can see the sample on the left had 14,995 come out rolls. You can see the distribution here. They're pretty close. For instance, this 7 rolled 2,491 times, and we would have expected 2,499, so that's pretty darn close. That actually works out to 16.61%. You know that the probability, true probability, is 16.67. The little graph looks very symmetrical and very triangular. It looks pretty good. The one on the right saw 14,909 come out rolls. You can see the distribution here, 2524 on the 7. We expected 2484, so this one's a little high. And we can see that reflected down here, 16.93%. Again, the graph looks pretty symmetrical and very triangular. So which runs are real and which ones are simulated? In this case, the real rolls are on the left. Now, is it possible to roll a higher percentage of 2, 3, 7, 11, and 12s on a come-out roll? Well, of course it is, especially at lower size samples. But is it going to happen every time? No, certainly not. Chances are both real and simulated numbers will display variation as expected, with averages converging on theoretical averages as the rolls increase. Now, what about streaks, clumps, and voids? Recently, another viewer claimed that WinCraps too often rolled streaks of 7 or 8 sevens in a row. Well, let's take a look at that. I've written a small AutoBet script that tracks streaks of 7s in a row. Once again, it has a few lines of initialization. It just clears the check stacks and gives them some names. And it's a very short little script here. It just says if the dice total is equal to 7, then let's increment a counter. That counter, we're calling it check stack 0 streak length. And for instance, if we rolled a 7, that counter would become a value of 1. If the next roll were also a 7, the counter would become a value of 2. If the next roll were 3, then it would drop down here and it would say, was it greater than 0? If so, then let's record the value of the counter on another check stack. So if, for instance, the check stack length, streak length was 2, then check stack number 2 is going to record the length, how many 7s were rolled twice in a row. And then it's going to reset the counter and go over. That's it, pretty basic. So let's activate that. Let's start a fresh simulation. So we're going to have clear data, clean data. Let's open the check stack screen. And here we can see those were the initialization lines. They just set up those names so we have something to look at. And let's start the hyperdrive. All right, notice how it's starting to fill in. It looks like there's having a fair amount of 7s that are by themselves, single 7s. Then we have some streaks of 2 7s in a row, and so far we've got 6 streaks of 3 7s in a row, and actually by now we had one time where we rolled 5 7s in a row. Let's stop the hyperdrive for a minute. Let's close this screen and we'll run the hyperdrive so we can collect some more data quicker. All right, there's 20,000 rolls. Let's look at the check stack screen again. All right, now we see that there were 2,374 times we had a single 7, 406 times there were 2 7s in a row, 67 times for 3, 13 for 4, 2 for 5. So as the number of rolls increase, the probability that we're going to see longer and longer streaks of 7s in a row increases. So what I've done now is I've created another picture to look at that has recorded the real rolls versus simulated rolls. So which is which? Which ones are real and which ones are simulated? The first sample here is at 50 rolls. We can see that this one had 6 7s by themselves. The sample on the right had 7, plus it had one instance of 2 7s. At 5,000 rolls, we can see we have 593 and 106, 21, 2, 2. So there were one. Let me make this smaller so I can see it. There was 2 instances of 5 7s in a row. On the right sample, there was only one instance of 5 in a row. Now let's look at 50,000 rolls. We can see the actual numbers here, and we can see they look fairly comparable on both sides. Both of these are sitting up around 57, 5,800. Second, two 7s in a row, both around 900 and something. 3 7s in a row are 160 versus 168. Then we get to 4, 29 versus 20, 5, we have 4s. And at 6, the sample on the left actually has one instance of 6 7s in a row, and the sample on the right does not have it. Now I went ahead and loaded another file that you can get on cloudcitysoftware.com. It's called randorg200k, and it contains 200,000 rolls that are created from real random samples. And I've compared that here. So here we can see this one on the left actually reached one instance of 7 7s in a row. And the sample on the right also had one instance of 7 7s in a row. So which ones are real? Can you tell? And in this case, actually, the real rolls are on the left. So here's another cross-check. Let's open up the AutoBet screen here again, where I've just written a couple little things here showing the formula. In order to compute the probability of 7s appearing in a row, you just multiply the probability of a 7 times the number of times in a row. So for example, if we wanted to look at 2 7s in a row, we would say probability of a 7 raised to the second power. So probability of a 7 times, that's 1/6 times 1/6, that's 1/36. What we do then is we take the reciprocal of that. So 1 divided by that amount, and that ends up being 36 rolls. Now that's also the same here as raising 6 to the power. So 6 to the second power. So we should expect to see 2 7s in a row once every 36 rolls. Now how about, let's think about those last samples we looked at. We saw 7 7s in a row. How often should you see that? Well, if you raise the probability of 7 to the 7th power, take the reciprocal of that, we should expect to see 7 7s in a row once every 279,936 rolls. So what did we actually see? Make this bigger again. We saw that was 200,000 rolls. We had one instance. So that's looking pretty much what was expected. Now, out of 279,000 rolls, we shouldn't necessarily expect to see 279,000 rolls go by and then a streak appears. It's just saying that on average, within the 279,000 rolls, there should be about one streak of 7 7s. So they could occur right off the bat, or they could occur much later in the sequence. You really don't know. But here it does look like they are pretty much in line with expectation. So I ask again, which ones are real, which ones are simulated? Well, I think I already told you that real ones are on the left. So it's very easy to change that script if you want to track some different numbers or even groups of numbers. Another feature at our disposal is the roll frequencies screen from the statistics menu. Let's take a look at that. What this screen does is it records the frequency. It records each time a number is rolled, and it records how frequent it appears. So for instance, let's take a look at this number here, 37 and 1. What this means is that 36 rolls went by without the appearance of a 7, and then a 7 appeared. Now the reason I say 7, of course, is going to have it selected up here. So it appeared on the 37th roll. Down here, let's pick out this one here. There were 217 times that 6 rolls went by without a 7, and then the 7 appeared. There were 587 times that 7s rolled back to back. So that kind of gives you an idea of the distribution. So the chances of a very long roll without 7s, you can see, is not that great. The greatest number here so far that we rolled out of 20,000 rolls was 3 instances of 42 no 7s followed by a 7. Now, as we increase the number of rolls, of course, the probability that we get higher and higher numbers increases. Let's take a look now at some more data that I collected. And we'll start out with the frequencies of number 7, RNG number 1 versus RAND-ORG 100K. These samples are taken at 50,000 rolls. Which ones are real, which ones are simulated? Let's look at the data here for the number 7. Sample on the left, there was one instance where we actually reached 59 rolls before the 7 appeared. Sample on the right, looks like the highest one was 44. 44 rolls before the 7 appeared. The number of 7s that appeared back to back, 1392 versus 1408. You can kind of go through these numbers and see how proportionally they look very similar. They decrease as the number of rolls go up. So which ones are real, which ones are simulated? I'll tell you in just a moment. Let's look now at the frequencies for the number 2. The number 2 does not appear as often as the 7, has a smaller probability, and so the numbers can be much more spread out. Here on the left, we see that the number 2, actually 2 times, it went over 200 rolls before it appeared. Now the screen actually has a limitation of 200 rolls. If you would like to find out the exact number of rolls, you can write a little AutoBet script, and you can determine what that is. The sample on the right had 3 instances where it went over 200 rolls before the 2 appeared. Once again, you can look at the numbers, you can look at the distribution, you can look at how they start big at number 1 and then kind of decrease as they go through. Compare both graphs, both tables, left and right, and you see that they're very, very similar. It's very difficult to tell which are real and which are simulated. In this case, the real rolls are on the left. Here's another little check. Have you ever heard the expression, see a horn, bet a horn? Such a question would lead you to believe that the probability of hitting a horn is greater following another horn, right? So let's see if that's true, and let's compare real versus simulated rolls. This script, again, has a few lines of initialization, clearing some check stacks and giving some names. And then all it does is it looks and says, is the dice total either 2, 3, 11, or 12? If it is, first thing we're going to do is increment a counter to count how many horns there were. And then we're going to say if there was a previous horn, then we're going to bet $4 on horn because we're claiming that it's more frequent, right? There's a higher chance that it's going to roll now. So we want to make a bet on a horn. We're going to add 1 to a check stack that's going to give us a little information of how many horns followed other horns. And then we're going to do a little percentage calculation. You'll see it in a minute. So then it's going to say check stack 0 at previous is true. That just means that the horn number rolled, so the next time you can come through, you can see if the previous one was a horn or not. If the previous roll was not a horn, that value becomes false. So let's activate that. And we can come back to the main screen here, clear out the previous data. And let's just run the hyperdrive for a few minutes. Okay, there's 11,000 rolls. And let's take a look at the check stack screen, see what we got. All right, out of this 11,000 roll sample, we saw 1,807 horn numbers. Of those, 297 of them followed other horn numbers. That equates to 16.4361%. Now, there are 6 horn numbers out of every 36 rolls, so the probability of hitting a horn number is exactly the same as the probability of hitting a 7, 6 out of 36. That's 16.67%. So if we've rolled 16.43% of horn numbers and we expected 16.67, does that look terribly promising to you? That looks pretty much in line with probability to me. Now, once again, I've recorded some data here with the RNG number 1 versus RandOrg 200K, because we run 200,000 rolls here. And what I've done is taken that little check stack screen we just saw, and I clipped it and put it on top of the bet results screen. So for instance, on the left-hand side here, we can see that there were 33,327 horn numbers, 5,486 of them followed other horn numbers, and that's when we start making bets. So that 5486 you can see appears down here in the number of wagers. And after making those wagers, we see a net loss of 15.91%. The expected loss at this point should have been 12.5%. So it doesn't exactly look like we're making a lot of money here. How about the sample on the right? 33,387 horn numbers, 5,618 of them followed other horn numbers for 16.82%. Again, that looks pretty much in line with probability. So we look at the 5,618 wagers down here. It had a loss of 12.6%. Again, the expected was 12.5, so it's actually a little bit closer to expectation. So which ones are real, which ones are simulated? In this case, the simulated rolls are on the left. So actually, the simulated ones are a little bit further from expected probability than the real ones are a little bit further from probability from the real ones. You know, I might have said that wrong. Let me just repeat it. The real rolls here are on the left, and the simulated ones are on the right. How about this one? Another user complained that WinCraps would never go more than 29 rolls without a 7. Could it be true? Let me open up another AutoBet file here. It's a very simple script. It just has one line. It says if the number of rolls since the 7 is greater than or equal to 29, then bet $1 on 7. So if we're claiming or thinking that no 7s are going to appear, excuse me, let me repeat that there are no sequences beyond 29 rolls without 7s, that means that we can go 29 rolls and bet on the 7, and we have a very high probability of winning, right? So let's activate this. Let me make sure everything else is deactivated, and then we'll activate this one. We'll clear out the previous data. And now we're going to, let's see, let's run our hyperdrive. There's about 15,000, 16,000 rolls. Let's look at the bet results screen. Okay, so we have no 7s and 29s selected. All the bets are selected. And we can see that out of this 16,000 roll sample, there were 109 times where we made the bet. And what is our results? We lost 31.19%. Our expectation was 16.67. So we actually lost a much greater percentage than we would have expected. Now let's try looking at another picture that I've made here that has a greater number of rolls, and we can see what that looks like. So again, RNG number 1 versus RandOrg 100K. And we can see the sample on the left. There were 242 instances where we made bets, and the result was minus 15.28%. Expectation was minus 16.67. So that's a little low. Sample on the right, there were 289 times we made the bet, resulting in minus 22.14%. Again, the expectation minus 16.67. So this is a little bit high. So which ones are real? Which ones are simulated? In fact, in this one, the real rolls are on the right. So it really looks like that claim didn't pan out. Fact is, we could also have checked this on the roll frequencies page for the number 7. Remember we looked at that? So here are roll frequencies for the number 7. We can see that indeed there are sequences beyond 29 rolls where the 7 hit. And we could have just looked at that page right there. The real acid test of simulated versus real numbers is to run a battery of strategies against them. With craps bets being structured both for and against the dice, and with very small house advantages, any biases will be easily revealed and exploited. To do that, and I'm sure you'll find, just as we have here, that simulated numbers are statistically significant and for all practical purposes indistinguishable from real numbers. One of the reasons real simulated numbers sometimes get a bad rap is due to people's perceptions. Humans are good at detecting patterns, but notoriously bad at detecting random sequences. Sometimes truly random numbers can look like they have a pattern, and quite often humans will reject them because they believe they can't possibly be random. Another problem plaguing the perception of simulated numbers is time compression. Play in a casino for 3 hours at an average of 2 rolls per minute, and your chances of seeing 5 7s in a row are very small. But run a simulator on hyperdrive for a few minutes at 600,000 rolls per minute, and your chances are quite large. Often the unfortunate conclusion is that the simulator is flawed. Understandably, there are still perfectionists who won't accept anything less than real random rolls. No problem. You always have the options of rolling your own dice and inputting them into the game, or utilizing dice roll files created from real random sources such as the one we used here. My goal isn't to convince everyone that simulated rolls are a panacea and they must be used, but merely to point out that many claims about them are unfounded and that they can provide meaningful data. Thanks for watching, and good luck rolling. Bye.